Welcome to this problem walkthrough. In this session, we'll dive into problem number 1255, maximum score words formed by letters. We'll break down the problem, explore different approaches, and analyze their efficiency. Let's get started. In this problem, you are given three inputs: a list of words, a list of letters, and a score table for the English alphabet. Your task is to determine the maximum score you can achieve by selecting a subset of the given words. The key constraints are that each letter can only be used once, and a word can only be formed if you have enough of each required letter in the input list of letters. For example, if a word requires two A's, you must have at least two A's available to include that word in your subset. The scoring system assigns a specific integer value to each letter, so the challenge is to maximize the total score by strategically selecting words that can be formed. Let's look at an example to understand this better. Suppose the list of words is dog, cat, dad, good, and the available letters are C, D, D, G, O, O. Each letter has a corresponding score, as defined in the given score table. Here, the word dad has a score of 11 because the letters D, and D contribute scores of 5, 1, and 5, respectively. Similarly, the word good has a score of 10, with the letters contributing scores of 3, 2, 2, and 3. Together, forming the words dad and good gives the maximum total score of 23. This is because these two words are the highest scoring subset that can be formed using the available letters. Now consider a different example where the words are XXXC, AX, BX, CX, and the available letters are Z, B, C, X, X, X. In this case, the score table assigns a value of 4 to every letter. Here, the words AX, BX, and CX can each be formed, and each yields a score of 8. However, the word XXXZ cannot be formed because there aren't enough X letters available. By selecting the words AX, BX, and CX, the maximum possible score is 24. This example highlights the importance of carefully choosing subsets to maximize the score while adhering to the constraints. In another example, the word list contains only LeetCode, while the available letters are L, E, T, C, O, D, E. The score table assigns values to each letter, but in this case, the word LeetCode cannot be formed. This is because the word requires two E's, but only one E is available in the provided list of letters. Since no other words are present, and LeetCode cannot be constructed, the maximum score in this scenario is 0. This demonstrates how the availability of letters directly impacts the ability to form words and achieve a non-zero score. When solving this problem, it's essential to consider a few key edge cases. First, there may be scenarios where no valid words can be formed due to unavailable letters, resulting in a score of 0. Second, the solution must account for the frequency of each letter in the input, ensuring that letters are not overused. Third, if all the words in the list can be formed, the goal is to identify the subset of words that yields the highest possible score. Finally, the problem requires exploring all possible subsets of words, which introduces a need for efficient algorithms to handle the constraints and maximize the score effectively. To tackle this problem, we first consider the brute force approach. The idea here is to generate all possible subsets of the given words, which amounts to 2 to the power of n subsets where n is the total number of words. For each subset, we then verify if it can be formed using the available letters. This step involves checking the frequency of each letter in the subset and ensuring it does not exceed the count of available letters. If a subset is valid, we calculate its total score using the given score table, and among all valid subsets, we return the one with the maximum score. However, this approach has significant drawbacks. Generating all subsets is computationally expensive, requiring 2 to the power of n operations. Additionally, validating each subset adds another and asterisk 26 complexity, where 26 represents the number of letters in the alphabet. The total complexity becomes 2 to the power of n times 26, which is impractical for larger inputs due to its exponential growth. This inefficiency highlights the need for a more optimized solution. To improve upon the brute force method, we turn to an optimized backtracking approach. This strategy dynamically explores subsets of words while enforcing constraints on letter usage, eliminating the need to generate all subsets upfront. Backtracking works by systematically making decisions whether to include or exclude a word while keeping track of the running score and the remaining letter counts. At each step, we first verify if the current word can be formed using the available letters. If it cannot, we skip it. If it can, we temporarily update the letter count and add the word score to our running total before recursing to the next word. After exploring a choice, we backtrack by restoring the previous letter count and score, ensuring we maintain correctness for subsequent decisions. This process continues until all possible paths are explored, and we track the highest score encountered. While the worst-case complexity remains 2 to the power of n, pruning invalid paths early significantly reduces the actual number of computations, making this approach much more efficient in practice. One of the primary advantages of the backtracking approach is that it avoids the need to generate all subsets in advance. By dynamically building solutions and pruning invalid paths as soon as constraints are violated, we save a significant amount of computation time. As an alternative, a greedy approach could be considered, where we prioritize words based on their score-to-letter ratio. While this might seem efficient, it comes with major limitations. Greedy algorithms often fail to account for dependencies between words and the constraints imposed by limited letter availability. This means they are unlikely to find the globally optimal solution in this problem. As a result, the greedy approach is not well suited here, given the complexity of the constraints and the need for accuracy in maximizing the score. After evaluating the options, the optimized backtracking approach emerges as the most suitable strategy for this problem. Brute force, though correct, is computationally infeasible due to its exponential complexity. On the other hand, the greedy approach, while faster, fails to guarantee an optimal solution because it relies on heuristics that overlook critical constraints. Backtracking strikes the perfect balance between correctness and efficiency. By dynamically exploring valid subsets and pruning paths early, it leverages the problem's structure to significantly reduce the solution space. Key observations support this choice. Letter constraints naturally limit the number of feasible solutions, and the subset formation process aligns closely with the recursive nature of backtracking. While backtracking is slower than the greedy method, it ensures optimality and is exponentially faster than brute force. In conclusion, this approach effectively balances trade-offs, making it the best fit for solving the problem accurately and efficiently. To begin, the goal of this problem is to maximize the score from subsets of words that can be formed using a limited supply of letters, while respecting a scoring table that assigns a specific value to each letter. The challenge here is twofold: determining which subsets of words are valid, meaning they don't exceed the available letter counts, and efficiently calculating the scores for these subsets. The algorithm starts with parsing the input. This involves reading the list of words, the available letters along with their frequencies, and the scoring table that maps each letter to its score. Once the input is processed, we generate all possible subsets of words. By using a bit masking approach, we can represent each subset as a unique combination of words. For n words, there are 2n possible subsets, and we systematically explore each one to determine if it can be formed using the available letters. After generating all possible subsets, the next step is to validate each one. For every subset, we calculate the frequency of each letter used by the words in that subset. These frequencies are then compared to the available letter pool, ensuring that no letter exceeds its allowed count. If a subset is found to be invalid, it is discarded immediately. For valid subsets, we proceed to calculate their scores. This is done by summing up the scores of all letters in the subset, based on the predefined scoring table. Throughout this process, we keep track of the maximum score that has been encountered so far. Once all subsets have been evaluated, the highest score is returned as the result. One of the key insights in this algorithm is the use of bit masking to generate subsets. By representing each subset as an n-bit integer, where each bit indicates the presence or absence of a word, we can efficiently iterate through all possible combinations without needing to explicitly store them. Another important insight is the validation of subsets using letter frequencies. By maintaining a count of the letters used in each subset, we can quickly determine its validity in constant time relative to the size of the alphabet. Finally, the scoring table enables efficient calculation of subset scores. Since the score for each letter is pre-computed, we avoid redundant calculations and can sum letter scores quickly. The algorithm relies on 3 key data structures to achieve its efficiency. First, dictionaries are used to track letter frequencies, both for the available pool of letters and for the current subset being evaluated. For example, a dictionary like A2B1 allows us to quickly check the counts of letters. Second, the scoring table is implemented as a dictionary that maps each letter to its score, such as A1, B3. This ensures fast lookups when calculating subset scores. Lastly, bit masks are used to represent subsets of words. For instance, in a set of 3 words, the bit mask 101, or the integer 5, represents the subset that includes the first and third words. This representation is compact and enables efficient subset generation. The operations in this algorithm have varying complexities, which are worth understanding. Generating all subsets has a complexity of 2 to the power of n, where n is the number of words, because there are 2n possible combinations of subsets. Subset validation involves comparing letter frequencies, which takes k time per subset, where k is the number of unique letters. Since k is constant, this step remains efficient. Similarly, score calculation for valid subsets also takes k time, as it involves summing the pre-computed scores of the letters. When combining these operations, the overall complexity of the algorithm is 2 to the power of n * k, which reflects the exponential growth in the number of subsets as the number of words increases, but with efficient validation and scoring for each subset. To further optimize the algorithm, there are several strategies we can apply. First, we can implement early pruning, which stops processing a subset as soon as it exceeds the available letter count. This prevents unnecessary calculations for subsets that are guaranteed to be invalid. Second, memoization can be used to store the scores of previously validated subsets, avoiding redundant computations when the same subset or a similar configuration is encountered. Finally, we can sort the words based on their potential maximum scores before generating subsets. By prioritizing high-scoring words, we increase the likelihood of finding optimal solutions earlier in the process, which can save computational resources. Here, we start by importing the counter class from the collections module, which will help us efficiently count the frequency of letters. Inside our solution class, we define the main function, maxScoreWords. This function takes 3 parameters: words, which is a list of words we can use, letters, which is the collection of available letters, and score, which is a list that maps each letter to its respective score. The first step is to create a letter_count variable using counter to store the frequency of each available letter. Then, we define a helper function, calculate_word_score, which computes the score of a word by summing up the scores of its individual letters based on the score table. Following that, we define another helper function, can_form_word, which checks if a given word can be formed using the available letters. It does this by comparing the frequency of each letter in the word to the frequency of that letter in the available pool. If any letter in the word exceeds the available count, the function returns false, otherwise, it returns true. Finally, we define a recursive function, DFS, which uses depth-first search to explore all possible subsets of words. Inside DFS, we first check the base case. If the index reaches the end of the words list, we return the current score. Then, we calculate the maximum score by initially skipping the current word and recursively calling DFS on the next index. Now, we proceed to handle the scenario where we include the current word, provided it can be formed with the available letters. We retrieve the current word using the index, and if the can_form_word function returns true for this word, we proceed to subtract the frequencies of its letters from the available pool using a counter. We then recursively call DFS, adding the word's calculated score to the current score and updating the maximum score accordingly. After this, we backtrack by restoring the letter frequencies to their original state, ensuring that other recursive paths remain unaffected. Finally, the DFS function returns the maximum score obtained either by including or skipping the word at the current index. To kick off this recursive process, we call DFS with an initial index of 0, the full letter_count dictionary, and a starting score of 0. The function then explores all possible subsets of words and returns the highest score achievable. This completes the Python implementation for the maximum score words problem. Here, we start by defining our solution class and the main function maxScoreWords. The goal of this function is to calculate the maximum score we can achieve by forming words using the given letters and their associated scores. First, we count the frequency of all the available letters using a hash map. This allows us to efficiently track how many times each letter can be used. Next, we define a helper function called calculateWordScore. This function takes a word and the score array as inputs and computes the total score of the word by summing up the scores of its individual letters. Each letter's score is determined by using its position in the alphabet as an index in the score array. We then define another helper function called canFormWord. This function determines if a given word can be constructed with the available letters. It does this by iterating through the word's characters, counting their occurrences, and checking if those counts exceed the available supply in our letter map. If any character in the word cannot be formed with the available letters, the function returns false. Otherwise, it returns true. These helper functions set the foundation for solving the problem recursively. After defining the helper functions, we implement a recursive function DFS to explore all possible subsets of words. This function takes the current index of the word being considered, the map of available letters, and the current score as inputs. The base case for the recursion is when the index reaches the end of the word's array. At that point, the function simply returns the current score as there's nothing more to process. From here, we explore two choices for each word. First, we skip the current word entirely and calculate the maximum score by moving to the next index. Then, we consider including the current word in our subset, but only if it's possible to form the word with the available letters. To do this, we create a count map for the word, subtract the required letters from the available ones, and calculate the new score using the calculateWordScore function. After this, we make a recursive call to explore further subsets while including the current word. However, since we modified the available letters map, we need to backtrack by restoring the original counts for the letters to ensure the changes don't affect other branches of the recursion. The backtracking step is achieved by iterating through the letters used in the current word and restoring their counts in the available letters map. This ensures that the recursive exploration of other subsets remains unaffected by the decisions made for the current word. Once both choices for the current word, skipping it or including it, have been explored, we return the maximum score obtained from these two paths. Finally, the entire process begins with an initial call to the DFS function, starting at index 0, with the full set of available letters and an initial score of 0. The function then explores all possible subsets of words recursively, calculating the maximum score that can be achieved. This implementation combines recursion, backtracking, and helper functions to efficiently solve the problem while ensuring correctness at each step. Here, we start with a basic example to understand the solution. The input includes the words dog, cat, dad, and good, along with the available letters and their scores. First, we construct a letter_count dictionary, which tells us how many of each letter we have available. For this input, it results in a 2, C1, D2, G1, O2. Using this, we begin our depth-first search, DFS, process from the first word, with all letters available and an initial score of 0. The first word, dog, can be formed because all the required letters are present. Calculating the score for dog, we get 5 points for D, 3 for O, and 2 for G, which totals 10. We then update the available letters, reducing the counts for D, O, and G, and proceed to evaluate the next word, carrying forward the current score of 10. The next word, cat, can also be formed since all the required letters are still available, C, A, and T. Calculating its score, we get 9 for C, 1 for A, and 0 for T, adding another 10 points to the score. After forming cat, we update the available dictionary to reflect the letters left, which results in a 1, C, 0, D, 1, O, 1. With this, we move forward to the next word while carrying a cumulative score of 20. At this point, the DFS process explores all possible combinations of forming and skipping words, including dad and good. Once all branches are explored, the algorithm backtracks to reset the available letters and the current score to their previous states, enabling it to evaluate other combinations. After checking all possible paths, the algorithm determines that the maximum score achievable is 23, which can be obtained by choosing the words dog and dad. This demonstrates how the DFS approach efficiently evaluates all potential solutions to find the optimal one. Now, we look at an edge case where no valid words can be formed. The input includes the words apple, banana, and grape, but the available letters are only X, Y, and Z. After constructing the letter underscore count, we see that it contains only x1, y1, z1, which doesn't match any of the letters required by the given words. Starting the DFS process, the algorithm first checks Apple and finds that it's impossible to form since it requires letters like A and P, which are not available. Similarly, the word banana is skipped because it requires 3 A's and other letters that are missing. Finally, grape is evaluated, but it too cannot be formed since it requires a G, which isn't available. As no words can be formed, the algorithm concludes that the maximum score is 0 for this input. Finally, we consider an example where all words can be formed. Here, the words are of B and C, and the available letters are exactly A, B, and C, with corresponding scores of 1, 2, and 3. Constructing the letter underscore count gives a 1, B1, C1, which matches perfectly with the letter requirements of the words. The DFS process begins by evaluating the first word, A, which can be formed using 1A, resulting in a score of 1. The available letters are updated to A, 0, B, 1, C, 1, and the algorithm proceeds to the next word. The word B is formed next, contributing 2 points to the total score, and the available letters are updated again. Finally, the word C is formed, adding 3 more points. With all words formed, the maximum score achieved is 6, demonstrating how the algorithm can handle cases where all options are viable and maximize the score effectively. To analyze the time complexity of our solution, we start by looking at the depth-first search, or DFS, approach used to explore all possible subsets of the words list. Since each word can either be included or excluded in a subset, there are 2n total subsets if there are n words. This means the DFS recursion has a time complexity of O2 to the power of n. Next, we consider the can_form_word function, used to check if a word can be formed from the available letters. This function uses a counter to compare character frequencies in the word with the available letters. If the average word length is k, this operation has a time complexity of O(k). Since we call can_form_word for every subset, the total time complexity includes this step as well. Now, let's look at the calculate_word_score function, which computes the score of a word by summing up the scores of its individual characters. For a word of length k, this operation takes k time. This step is only performed for valid words within each subset. Putting it all together, the DFS explores all 2n subsets, and for each subset, we perform k operations for both can_form_word and calculate_word_score. Therefore, the total worst-case time complexity of the solution is O2 to the power of n*k. The space complexity of the solution is determined by several factors. First, the DFS recursion tree has a maximum depth of n, corresponding to the number of words, requiring n space for the recursion stack. Then, we consider the counter object used to store the frequencies of available letters. If there are m unique letters, this requires m space. Similarly, the word underscore count counter used in can_form_word also takes up to m space in the worst case, as it also depends on the number of unique letters. Temporary variables like word underscore count and max underscore score are reused during each DFS call, so they do not add to the overall space complexity. These factors together determine the auxiliary space usage of the solution. When we combine all these factors, the total space complexity of the solution is n plus m. In the best-case scenario, if the words list is empty or there are no valid subsets, the DFS terminates immediately. Here, the time complexity reduces to 1, and the space complexity is dominated by the available counter, resulting in m. In the average case, the DFS explores some valid subsets, but not all 2n subsets. The time complexity in this case depends on the number of valid subsets, which is generally less than the worst case. In the worst case, the DFS explores all 2n subsets, and for each subset, it performs k operations. This gives a time complexity of O2 to the power of n*k, and a space complexity of n plus m. Finally, let's compare this optimized DFS approach with a naive brute force solution. A naive approach would explicitly generate all subsets and check each one for validity, resulting in both time and space complexities of O2 to the power of n*k. The optimized DFS solution, on the other hand, dynamically explores the subsets using recursion, avoiding the need to explicitly store all subsets and reducing memory usage to O, n plus m. However, the time complexity remains the same at O, 2 to the power of n asterisk k. Mathematically, this makes sense because the DFS ensures all 2 caret n subsets are explored, and for each subset, can_form_word and calculate_word_score each O, k, are called. The space complexity is determined by the recursion stack, O, n, and the letter counters, O, m, leading to a total space complexity of O, n plus m. When solving this problem, there are several common mistakes to watch out for. First, overlooking edge cases can be a major source of errors. You need to consider scenarios like empty strings, very large inputs, or cases where no valid subsets can be formed. These edge cases should always be part of your testing process. Next, an inefficient brute force implementation can slow down your solution significantly. If you generate all possible subsets without pruning invalid ones early, you'll waste time on unnecessary computations, especially when working with large input sizes. It's crucial to optimize by stopping as soon as constraints are violated. Another pitfall is handling letter frequencies incorrectly. For instance, if a word requires a letter twice but you only have one available in the pool, your solution needs to catch this mismatch accurately. Additionally, ignoring opportunities for optimization, such as using memoization or caching, can lead to redundant calculations. For example, subsets formed from the same input can often be reused rather than recalculated. Finally, misjudging the complexity of subset generation is something to avoid. Generating subsets has an exponential time complexity of O, 2 to the power of n, where n is the number of words, so it's important to keep this in mind and respect the problem's constraints and limitations. Now, when it comes to interviews, there are specific insights that can help you stand out. First, focus on early pruning. Interviewers often evaluate how efficiently you can skip invalid branches in the solution space. This demonstrates your ability to identify and eliminate unnecessary computations. Also, discussing trade-offs is essential. Be ready to compare brute force methods with more optimized approaches like backtracking or greedy algorithms, and explain when each one is appropriate based on the problem's constraints. Using examples is another great way to clarify your thought process. Walk through a small example to show how subsets are generated and validated step by step. This not only makes your explanation clearer but also highlights your understanding of the problem. Additionally, proactively addressing edge cases during your explanation shows thorough preparation and comprehension. Lastly, it's helpful to connect this problem to related ones, such as LeetCode 78, subsets, or LeetCode 90, subsets 2. These problems share similar patterns and techniques, so referencing them can demonstrate your broader problem-solving experience. There are also alternative approaches and trade-offs you can explore for this problem. The backtracking approach is a highly efficient option. Instead of generating all subsets, you build each subset recursively while validating constraints as you go. This avoids unnecessary computations, but the trade-off is a more complex implementation. Another option is the greedy approach. If the problem allows, you could use a heuristic to choose subsets, such as maximizing the use of available letters. This can be faster but doesn't always guarantee the optimal solution. Dynamic programming is another powerful approach. By solving the problem in a bottom-up manner, you can count ways to form subsets using the available letters. This method is great for problems with overlapping subproblems, though it may require significant memory. Finally, bitmasking is an efficient way to represent subsets and test constraints, especially for smaller input sizes. However, it can be tricky to implement and debug due to the complexity of managing bit-level operations. Each of these approaches has its strengths and weaknesses, so the best choice often depends on the specific constraints and requirements of the problem you're tackling. Great job making it to the end. We've covered the problem, explored approaches, and analyzed their complexities. Remember to practice and apply these concepts to similar challenges. If you found this helpful, like and subscribe for more problem-solving insights. See you next time. That's the end of this tutorial. I hope you found this explanation helpful for understanding the solution to this LeetCode problem. If you enjoyed this content, please consider subscribing to the channel for more coding tutorials and solutions. Feel free to leave a like if this video helped you, and don't hesitate to comment with any questions you might have. Thanks for watching, and happy coding!